muted, by the way.
Thank you. There we go. I've been muted for the first 10 seconds. That's fine. I didn't say anything interesting. I think I just said hello and I said the name of the section. So there we go. So let's go over what we've learned so far, right? Because we've already learned a little bit about derivatives of some of these functions. In fact, we've got half of them down already. So what I told you so far is that the derivative of e to the x is itself. This is a very special function whose derivative is itself. I've considered going over like a proof of this, but any proof I could show you is going to be incomplete because there's a component of it which is sort of beyond the scope of this course. You know, you can certainly look at it from sort of numerical approach. Here's what I'll say. The thing we know about exponential functions in general is that their rate of growth is proportional to the function itself. So in general, the derivative of an a to the x exponential function, the rate of growth of an exponential function, is proportional to the original function. So there we go. So the letter K represents a constant of proportionality. You guys may have learned about proportional relationships in the past. Sometimes it's called variation, like it varies directly. Is that something you've learned about? And there's this constant of variation or constant of proportionality. Does that sound familiar?
No.
Okay. It just means that, here's the quick and dirty version of that if you've never heard of this. It just means that when two things are proportional, directly proportional, it means that one of them is a multiple of the other. That's it. One of them is like a constant multiple of the other.
Could you give a real life example?
Yeah. So a real life example would be like, oh man, the first one that comes to my mind is from physics, but it might be a little bit not very familiar. So I've been talking about it with my Calc1 class. It's an easy real life example. Like the amount of money you, so the amount of money that you spend on groceries is directly proportional to the quantity of groceries you buy. That's sort of a vague one because it's not entirely clear like what that constant would be, but let's have it be more specific. Like if you are buying meat, say you're buying like pounds of ground beef, something my wife and I do, we order meat from a farm. The amount of money that you have to pay is directly proportional to the number of pounds you buy. And the
nearest farm
is the price per pound.
The nearest farm?
No, it's sorry. I got distracted by no, we order meat from a farm. It's kind of far away, but they do a delivery.
Yeah, okay. I also have a question.
Does that make sense for all? It's just like there's a constant there and it's the price.
Yeah, but you said that one of them is a multiple of the other.
That's right.
So is the price a multiple of amount of pounds, or?
So the price is the constant multiple, right? Like
Okay.
when we say it's a multiple, the price is the multiple. So the amount you pay is a multiple of the number of pounds, where that multiple is like
for each pound,
$3.50 per pound or something like that. So that multiple can be thought of in that context as like a rate, right? Because it's price per pound, so that's a rate.
Okay, yeah, that makes sense. Thanks.
Okay. So in this context, what we're saying is here that an exponential function is a function whose growth rate is proportional to the value of the function. Now, what you can think of that as meaning is that as the function gets bigger, the growth rate also gets bigger by some multiple of the function. So let me just pull over a quick graph of one of these functions. You know, if you look at one of these functions, you can see as it gets bigger, the steepness of the curve is also getting bigger. So it grows faster as it grows. That make sense?
Kind of looks exponential, isn't it? Not really proportional.
Exactly, exponential. No, that's right. So like, so if the x and the y were proportional to each other, we would be talking about a straight line, right? But the difference here is that we're not talking about x and y being in proportion. That would be a straight line like this, right? We're talking about the let me get the visualization we want here. We want to have there we go. There's my tangent line. Okay. What we're saying is that the value of the function, the y value, the y output of the function is proportional to the slope of the tangent line. That's what we're saying. It's really hard to see. It's kind of hard to see that proportionality because it's not just like a straight line like you're used to seeing a proportional relationship. It's a little more subtle here. This is like the key defining feature of exponential functions, right? The rate of growth is proportional to the function itself. So they grow faster as they grow bigger. Exponential growth. I mean, that's what we call it. We call that exponential growth. And so exponential functions are the specific type of function that has that property. But then there's the question of like, well, what is that constant of proportionality? And the number e which I know the first, I don't know, 14 digits of. That number e, which is an irrational number, is the only number for which that constant of proportionality, k, is equal to 1. Okay, so rather than having to, rather than the rate of change being like 2 times the original function, or 1.5 times the original function, or like 2/3 of the original function, it's like 1 times the original function, straight up equal to the original function. And this is the only number for which that's true. It's the special shiny magic number that makes that work. And so that kind of that is the sort of story behind this fact right here, right? That e to the x is the function whose derivative is just straight up equal to itself without anything else. Now, what we learned more recently by using the chain rule was that if you have some other number, like anything other than e, or even e itself, I guess, but the more general version of this rule is it's a to the x times the natural log of a. And that natural log of a, by the way, is the constant of proportionality. That's k. Okay, it is a constant, right? So if you look at this right here, this is this. Okay, so through our exploration with the chain rule, that's when we discovered the exact way that this proportional relationship works. It's the constant of proportionality that relates the rate of change to the function's value is the natural log of the base. And that's so that's the second thing we learned. All right, so these are basically two differentiation rules that we can memorize. The second one is a proper generalization of the first one, and what that means is that the second one includes the first one as an example. So let's do a few examples. One is if you have like 2 to the power x, this would be 2 to the power x, but then times the natural log of 2. Another example is if you have e to the power x, this would be e to the power x times the natural log of e. So what I'm saying is that the first differentiation rule, this one, is like an example of the second one. And this is it right here. Now, you may be feeling a little confused because this is not identical to this. What's the difference?
There's an extra natural log of e, but they just cancel anyway.
Yeah, what is the natural log of e actually equal to?
1.
That's right, it's 1. And that's the key here. The idea is, yep, it is equal. It gives you the same answer as this rule because it's the natural log of e, which is 1. So yeah, so there we go. So that's pretty much kind of those are the two differentiation rules we've learned so far, and that's just a little more of the story behind these rules and like how it all comes from this sort of defining feature of exponential growth, okay, about the proportionality between the rate and the output. So I think it's time to talk about doing an inverse of this. So what we haven't learned how to do yet is take a derivative of a logarithm function. What about log of x? Or log base a, if we want to talk about a general sort of version of a logarithm. We'll start like we did with the exponential functions. We'll start with base e. Start with the natural log of x, right? Log base e, okay? In order to figure out the derivative of the natural log of x, we'll write an equation. We'll write y equals the natural log of x. And our goal is to find the derivative of y with respect to x, okay? But we don't know a differentiation rule for logarithms. However, what we do know we can do with logarithms is we can take an equation involving a log and rewrite it as an equation involving an exponential with the same base. So that would be a base e exponential. How do I take this equation and rewrite it with an exponential base e?
Can I ask a quick question?
Yes, of course.
Why is it this time we're finding the derivative of y with respect to x? And usually it's no, never mind. No. It's
That's
usually
okay. Yeah. This is the way it usually is. Yep. Yeah. Good to think that over. I'm glad you kind of went through the process of making sure that was the way it usually is. Okay, so we're inverting this equation, right? We want to get it with base exponential base e. Anyone remember how to do this?
With this,
switch it to e to the x power.
Hang on, that's kind of the idea, Adam, but let's hear what Boyd was saying.
so the given base of a natural log is e. So then you would bring the e from the natural log to the left side and have that e to the power of y is equal to x.
Yes, that's correct. Okay, yeah. So as Boyd said, it's e to the power y equals x. So it is using the e to the x function, except it's not x that's inside of it; it's the y that's inside of it. Okay. Yeah. This is, by the way, not that different from having something like y equals x cubed is the same as saying the cube root of y equals x, or like y equals 2x is the same as saying a half y equals x, or like y equals x plus 7 is the same as saying y minus 7 equals x. Okay, as you can see, all of these are examples of having a function on one side and then moving it over to the other side by inverting it, right? So like the inverse of times 2 is divided by 2, or times a half. The inverse of plus 7 is minus 7. The inverse of cubing is a cube root. The inverse of log is e to the power of something, right? This is also just moving something from one side to the other by inverting it. This is another example of the same idea. Okay. So anyway, just wanted to point that out. Now that we are here, now our goal is to find dy over dx. We have functions we know how to differentiate. Let's do implicit differentiation on this. So we'll do the derivative with respect to x of both sides. Okay, our goal is still this, but we're doing implicit differentiation to find dy over dx. So the right-hand side is the easy one. That's just equal to 1, right? Derivative of x with respect to x is just 1. The left-hand side, we have to use our special version of the chain rule for implicit differentiation. First, we can just differentiate e to the power y the way we usually do, which is like this. It's its own derivative, as noted earlier. But then we multiply by y prime, right? Because that's the chain rule. That's what we've been talking about with implicit differentiation. By the way, y prime and dy over dx are the same thing. So no matter what you want to call it, whether it's y prime or dy over dx, that's our goal, right? So then solving for dy over dx is very simple. It's just 1 over e to the power y, right? But
Yeah, but understand.
say what?
No, nothing.
Okay. This is a very simple algebra, right? Just to like divide by e to the power x or e to the power y. The problem is now this is not really a very good answer because it's in terms of y, which is not ideal. If we want to have like a derivative rule, right? If we want to say like the derivative of the natural log of x is blank. Usually when we find the derivative of a function of x, we get f prime of x. It's still in terms of x, right? So we want something with an x in it as our answer. So 1 over e to the y is an answer, but it's not a very good one. So what we want to like make some sort of substitution that can put this back in terms of x. So we go back to our original relationship we had. You know, remember that equation? E to the y and x are actually the same thing. So when we say 1 over e to the y, we might as well be saying 1 over x. Okay? And that's based on that relationship that e to the y and x are equal to each other. So when we have 1 over e to the y, that's actually 1 over x, and that is the answer we're really looking for here. That is our new differentiation rule for logarithms. The derivative of the natural log of x is 1 divided by x. Okay? So now that we know that, we can use it for things. Let me get rid of this jazz over here. I don't need you. Okay, let's do some examples. Do some nice little quick ones. Let's say you got like y equals x times the natural log of x. Woo! Product f times g, right? Well, if we want to find y prime, all we have to do is a little product rule. F prime times g plus f times g prime. Does that look familiar? We got that memorized. So we should be able to do this. F prime here is going to be just 1, right? Times g. G is the natural log of x, so I can just copy that in. Then we get, then we want just original f here is x. Oh, here's the plus, sorry. Original f here is x, and then we do g prime. And the derivative of our natural log of x we just learned is 1 over x. Okay, so the derivative of this x times ln of x is 1 times the natural log of x, which is that, plus x times 1 over x. And this just simplifies, doesn't it? X times 1 over x is just 1. So there's a derivative of a function using our new differentiation rule.
Oh, wait, I have a question.
Sure.
So the derivative of the natural log of x is 1 over x?
Correct.
Oh, okay.
Right there. Yep. Let's do one more example of using this. Let's do y equals the natural log of 5x. So now, what differentiation rule am I going to need to use on this one?
The constant rule.
Constant multiple rule? Not really, because yeah, this is definitely more of a chain rule one, because the 5 multiplication by 5 is inside the function, right? If it were outside, if it were like 5 times the natural log of x, I could just use the constant multiple rule. But it's not that, right? It's not on the outside. It's on the inside. So yeah, that's a chain rule. So this is our f. Oh, hang on. I'll do this. I'll write it out again. If this is our f of g of x right here, right? Then what we're going to get for y prime is we're going to get f prime of g times g prime. That sound familiar? Now, if I wanted to write this out in detail, I could say f of u is the natural log of u, and u equals 5x. Right? So f of u is natural log of u. So f prime of u is going to be 1 over u. That's what we just learned right here, right? That's this rule right here. Okay. Whereas here, this is my u is equal to g of x. This is this thing, this u prime, where g prime is just 5. Okay. So let's put the pieces together now. The first thing I have to do is f prime, but with a g of x plugged inside of it, right? So I would write 1 over u, except instead of writing u, I'm going to put the g of x, right? So it's 1 over 5x. Does that make sense? Does that make sense so far? 1 over the function that was inside the logarithm, right? Because it's the f prime of the original g of x. Okay, so then I say this part, and then I do the times g prime, which is times this derivative of this inner function. Derivative of 5x was just 5, so times 5, like that. And there's my answer. It's 1 over 5x times 5, which is 1 over x. Because the 5s cancel out. So there we go. That's a little bizarre. It's like the 5 didn't matter. The derivative of natural log of x is 1 over x, and the derivative of natural log of 5x is also 1 over x, which actually brings me back to Boyd's suggestion in the beginning, the constant rule. Maybe I misunderstood what you were suggesting, actually, because there is a way to use the constant rule, not the constant multiple rule, but the rule that says that the derivative of a constant is 0. There is actually a way to use that differentiation rule in this problem.
Tristan?
What's up, Pharrell?
So you found y prime equals 1 over 5x times 5, but then that's only f prime of gx right there, right?
Oh, no, the f prime of gx would be this part.
Okay, never mind.
And then this is the g prime.
Okay, never mind.
But then how did you get 1 over x equals to 1 over x?
The 5s cancel out, right? Because one of the 5s is in the denominator and the other 5 would be in the numerator, right? Because multiplying by 5 is like multiplying by 5 over 1. That make sense?
Yeah.
And there's a question in the chat. Does that answer? Does that address that question? I'm not quite sure. Okay, cool. Yeah. So this is kind of this is a little bit bizarre, right? Because it's like the 5 didn't matter, like I was saying earlier. So there's actually a way to look at this. The natural log of 5x. You know how I was telling you about the magic, like the magic power, like the superpower of. Oh, hey, Luca. Do you need to? Okay, you got to stay with mom, Luca. I'm sorry, I was just letting the dog in. I might have to help the kids here in a second. We'll see. I'll keep an ear open. Okay, so the superpower of logarithms is that they turn multiplication on the inside into addition on the outside. And then if I want to know y prime, I just have to do the derivative of these two individually. Like this, right? So if I'm differentiating this two terms, I first differentiate the natural log of 5, and then we differentiate the natural log of x. So now, what is this one? What's the derivative of the natural log of 5?
0.
0.
Yes, it's 0. Was anybody thinking 1/5? It's tempting. Come on. Okay. You can't decide if she wants to be in or out. It's tempting because the derivative of the natural log of x is 1 over x, but this isn't the natural log of x here. This is the natural log of 5. The whole thing is just a constant. This is just 0. So then we have 0 plus 1 over x, and that's still 1 over x. So yeah, so that's really maybe the explanation of like why it is that the natural log of 5x is still just 1 over x, and it doesn't matter that there was a 5 there, because putting a 5 multiple inside there is basically equivalent to just adding a constant term on the end of on the side, you know, and that, as we know, adding a constant doesn't change the derivative because of the fact that the constant's derivative is 0. Okay, so that was maybe a little more time spent on that than we needed to. Questions at the moment? Any questions?
I'm still a little bit confused on what you did for that problem. So where it was 1 over 5x, the one, okay, so f prime, if you could zoom in just a little bit, that'd be nice. So f prime is 1 over u, which is 1 over 5x.
Yep.
That's f prime.
Mm-hmm.
But then times g of x, right?
Of g of x. Yeah, this is composition of functions here. So we say, you know, f prime of g of x. This is so that whole thing would be so you could say it this way: f prime is 1 over u, and then you said, but that's 1 over 5x.
Yeah.
Right there, you're putting the g of x back inside of it.
Oh, okay. Okay. So it's not, okay, I got you. You're not multiplying by the g, okay.
No,
Yes.
you're sticking
Okay,
the g inside the f. Now this over here is multiplying. Then you're multiplying by g prime, and that's the 5.
Yeah. Yeah. Okay, that's where I was confused. Thanks.
Okay, cool. Yeah, good. I'm glad we cleared that up. Here comes the dog again. Come on in. You can stay this time. Maybe to solidify that, we could do one like this. This right here, natural log of x squared might be good because, or even we could do like, just to make it a little more, you know, x squared plus something maybe. We could say, oh, hey, let's take this derivative. This, we start by just doing 1 divided by whatever's inside here. So x squared plus 1, like that. And then we can say all of that times the derivative of x squared plus 1, whatever that ends up being, right? So this ends up being 1 over x squared plus 1 times 2x. And then if you want, you can take your 2x and you can just stick it in the numerator because it would be right up there times 1. So this is 2x divided by x squared plus 1.
Wait, I have a question. Why does it have to times by the derivative of x squared plus 1?
The chain rule.
Oh,
The chain rule, because whenever we are doing a derivative of whenever we're doing the derivative of, you know, a composition of functions like this, we always have the derivative of the outer function and then multiply by the derivative of the inner function. So that was this part. And this g of x here was this part. The f prime was the 1 over something. It's a color-coded version of seeing the different parts. Okay. Okay, so the question remains, what are we going to do with something like log base 3 of x? Okay, let's address that question. How do we differentiate something like log base something else? Log base 3. Log base, you know, actually log base 3 is very uncommon. Log base 10 might be a more common example, right? That is actually the common, what we call a common logarithm. It's used in a lot of sciences. Okay. So now that I've changed the base of the logarithm, I'm going to get a different derivative. So, in order to figure out what that is, I can use an identity here. This right here is called the change of base formula. You can write any logarithm with any base in terms of any other logarithm with any other base. If you're doing it, if you want to convert from base something like 10 to base e, the natural log, it looks like this. And what it is it's the log of the input divided by the log of the original base that you used to have, like that. Okay, so if this had been a log base 5, then we would have put a natural log of 5 in the denominator. Okay, this is the change of base formula. This comes from pre-calculus. I won't go over a proof of it or whatever, but that's a thing. Okay, and so then, but then like that log of 10 in the denominator is just a constant, right? So I could think of this as 1 over the natural log of 10 times the natural log of x, like that, right? And then I can apply the constant multiple rule and pull the 1 over natural log of 10 out of the derivative, like that. And now I just get 1 over the natural log of 10 times 1 over x. And I get for my final answer 1 over the product of natural log of 10 times x. Or I'm going to write it the other way around. Traditionally, we put the x first and the natural log of 10 second. I don't really know why. That just is the more comfortable way to write it for some reason. Maybe it makes it clear that the x is not inside of the logarithm, it's outside. It's like multiplied on the outside. I don't know. So there we go. So now this produces another new differentiation rule. Which is that the derivative of log base anything, log base a, you could say, of x, is always going to be 1 over x times the natural log of a. Like that. And this new differentiation rule is a generalization of the natural log of x differentiation rule in exactly the same way that this general exponential differentiation rule was a generalization of the original natural exponential rule, right? It encompasses, this new rule encompasses log base e, because again, you just have this factor of natural log of a, which if a equals e, natural log of e just equals 1. So it's that's what I mean by a generalization. It encompasses the specific case that we already established, but it also addresses every other case. So there we go. So now we have all 4 of the differentiation rules we need to differentiate any exponential or logarithmic function. Woo! Time for a new board. 16th today. Part 1. Okay, before too long, not quite yet, because I want you guys, so I'll explain. Before too long, I will give you this document. Or actually, I'm going to give you half of this document. I think I've showed you this before. Where is it? There we go. I'm going to give you the first half of this document soon. You're not going to be allowed to use this on your quizzes until we get to chapter 4. This is not going to be allowed on the quiz, the upcoming quiz for chapter 3. But I'll give it to you as a study tool. Okay. And I just wanted to pull it up now because it has the 4 of these rules laid out right here They're labeled 9, 10, 11, and 12. Okay, and actually I used the letter B for the base instead of the letter A for the base, but whatever, it's the same, just a different letter. So there they are, the exponential ones and the log ones. Okay. To be honest, we use the natural exponential and natural log about 10 times as often as the other ones. So 9 and 11 are the main rules we're going to be using in this class and moving forward, like Calc2 and so on. We use just those just so much more often than anything else because the natural, exponential, and log functions are the best ones. Okay. Get a new screen. Okay, so let's write down this
I have
new
a question.
rule we learned, and then go ahead and ask your question.
Will we be using that sheet for the test? For
So
the
I just
quiz?
said that. You can use it. You're not going to be able to use it for the quiz on chapter 3, which is the upcoming quiz B. But then in the future, you'll get to use it on quizzes. So once we get to chapter 4 and 5, you can use it. Okay. I'm going to show you an example of what I call an extended technique. Does anybody play an instrument? You know what extended techniques on instruments? It's not the standard. I think I've talked to you guys about this before. This is an analogy I use with all my classes. It's like it's not the standard stuff you learn. It's sort of like extra, like weird things like humming through your saxophone while you also play the saxophone, so that you can get like chords and stuff. Things like that, or like using the keys to go clickety clack and do some like percussion while you're also playing, or like the guy who beatboxes while he's playing a flute. You guys seen that? Those are like extended techniques, right? They're not part of the like, yeah. So logarithmic differentiation is sort of an extended technique of differentiation that you use in some rare circumstances to differentiate some messy, complicated functions. So let's look at an example of such a function. Let's find the derivative. We want to find the derivative of x to the power x. X to the power x is a wacky, weird function because it is it's not a power function because its exponent is not constant. It's also not an exponential function because its base is not constant. It's kind of both or neither. It's kind of both, right? It's where the base and the power are both a variable and they're the same variable. There's a whole classification of functions of this type. Anything where you have some function of x raised to the power another function of x. So things like 2x to the power x squared plus 7, or like sine of x to the power, x minus 3, or whatever. Anything like that where the base and the power are both functions of x. And for all of these type of functions, you can use this extended technique. And the way it works is you start by doing natural log to both sides of the equation. So you have to start with an equation. You have to start with like a y equals, okay? And then we do natural log of both sides. And then we apply log properties log, for example, log of a to the power b equals b times log a. That's the one we're going to apply. That property can be applied right here. And what we get is natural log of y equals x times the natural log of x. Okay. Then now we have a new equation. Okay, so let's appreciate the power of this logarithmic property. Now we have a new equation, which doesn't involve any powers, right? It used to have this exponentiation in it. It used to have x to the power x in it, right? This thing. But then we just got rid of that using this log property and turned that power into multiplying, which is much easier to work with, right? Because this, we can take a derivative of this just with the product rule. In fact, we already did. It was one of my examples I went over just like, 20 minutes ago. So what you get here, so our next step here is to differentiate. But because we have the natural log of y on the left side instead of just regular old y, we actually need to apply implicit differentiation. Okay, so on the left, we got 1 over y, derivative of the natural log of y. But because it's y, and we want to differentiate with respect to x, we have a times y prime, like that. Okay, now we differentiated x times natural log of x earlier. We got natural log of x plus 1. So I'll just go ahead and stick that out there. Okay, got that earlier.
Isn't that 2?
No.
No. It's because it's a natural log. Never mind.
Natural log of x plus 1. So, like I said, look back in the notes, previous page for that example. But now to solve for y, we got to multiply. So to solve for y prime, we have to multiply both sides by y, right? So times y. There we go. And that like moves this, over to here. And then we can say, okay, we've almost got our answer, except that y was equal to x to the power x originally, right? So we're going to apply this original equation, right, to actually replace y with x to the power x. So you substitute the original function in for y and get times x to the power x right there. And that is our derivative. Isn't that wild? So we went through this process of using logarithms on both sides of the equation, and we took advantage of these log properties, these superpowers of logarithms, right? That like simplify things. They turn exponents into multiples. They turn multiplication into addition. They like just sort of like drop everything down one level of complexity. And that's kind of amazing. So we do that with logarithms, and then we just do implicit differentiation and end up solving for y prime. This is a strategy which allows us to differentiate functions of this type, but it also can allow us to just differentiate other functions that you could use the quotient rule and the product rule and the chain rule and stuff. Like there's other functions that you could differentiate with the other rules, but it'd just be messy. And logarithmic differentiation allows us to use those powers of logarithms to like simplify stuff so that the derivative process is just kind of easier. And so yeah, it's a tool we use occasionally. Okay, like I said, an extended technique. It's not going to be something you have to use on every piece of music you play, right? It's like it's just for the occasional weird avant-garde modern thing. I'm running with the analogy, but it's like there's the occasional function that requires, or if not requires, maybe it is well served by this logarithmic differentiation. So occasionally we pull it out and use it. Just something to have in your back pocket. Okay. So that's it for the day, folks. See you tomorrow.